Oh, hi. My name is Dan Wertheimer. I'm at Berkeley. And my research group works on this question, are we alone? Is anybody out there? And I'm also the PI of a collaboration called CASPER, which is the Center for Astronomy, Signal Processing, and Electronics Research. And I want to tell you a little bit about both of these projects and how PRP has been helping us out and guiding us with this research. So in SETI, one of the big problems is one of the ideas is that we want to look for radio signals. So Earthlings send off all this radio and radar and navigational beacons and television signals. And I Love Lucy's gone past 10,000 stars. The nearby stars have seen The Simpsons. So maybe ET has something like that we could detect. If they're an advanced technology, maybe they have radar or GPS or television or something that we could detect. But there's a big problem is that we don't know what frequency to look at and what kind of signal it might be. And that takes a lot of computing power to look for all the different radio channels and all the different possible signal types and do a sensitive search. And so one way to solve this computing problem is to ask volunteers around the world to analyze the data for us. And you can build a big supercomputer that way to ask the volunteers. And you probably have heard of this project that we run called SETI at Home. And the way SETI at Home works is that we use a big telescope. For the last 20 years, we use this Arecibo Observatory. It's 1,000 feet across, a big radio telescope. And we collect a few petabytes of data. We store it at the National Energy Supercomputing Center in Oakland. And then we break the data up into little pieces. Everybody gets a different part of the sky to work on, and they download this the screensaver program that works on different operating systems or works on cell phones. And then it kind of uses the spare computing cycles to analyze the sky. And we got 8 million people doing this thing in 220 countries, and it made the most sensitive search ever. But the problem with this volunteer computing is that you can only do this kind of volunteer computing if you don't have a lot of data to send out, because it goes out over the edges of the internet to individual homes and schools. And so you can't process a lot of data. But it is good for things where you want to do intensive computing without a lot of data moving back and forth. And we developed a kind of general purpose infrastructure for volunteer computing that maybe you know about called BOINC. It's an open source project, as is SETI at Home. And now you can use your computer to participate in 100 different science projects. We call it the democratization of scientific supercomputing. So you can use your home computer to look for malaria drugs or COVID-19 therapeutics or cancer drugs, or you can do climate change work, climate prediction. You can do gravity waves, pulsars, all kinds of projects, and you can choose which projects you're interested in. But there's another kind of problem that we have where you have so much data that you have to process it at the observatory. So each one of these telescopes puts out about 100 gigabits per second, and we might someday have thousands of these dishes. And so we have petabits per second. There's no way to record that and send it out and to volunteers around the world. So what we've been working on is kind of in situ high performance computing or high performance signal processing. And the architecture that we've been using is kind of a standard architecture that a lot of you are familiar with, but the way that radio astronomers have traditionally built these kind of high performance machines is dedicated ASICs and custom boards and custom interconnect. And we kind of changed that architecture to something that you guys are much more familiar with. We call them Ethernet telescopes or CASPER telescopes. And what we do is we digitize the data from each antenna, and very quickly we get that data into Ethernet packets, timestamp UDP packets. And those packets are sent into a big switch, typically a 100 gigabit switch. And then on the back of the switch, you have a lot of computing resources, typically a lot of FPGA resources and GPUs. And the nice thing about this architecture, as you guys appreciate, is that it's very scalable and upgradable and fault tolerant. And what astronomers like is that they can repartition this these computing resources to do what they want to do that hour. They can do spectral imaging or search for pulsars or do ET, or if there are enough computing resources, they can do all of those things simultaneously. And so a lot of people are using that architecture. It's called the Collaboration for Radio Astronomy Signal Processing Electronics Research, and it's used at most radio observatories. And it's led to a lot of discoveries. You might have seen these images of black hole that came out a couple of years ago. The first images of black holes. They discovered, these CASPER instruments discovered fast radio bursts. They found a lot of pulsars, and they discovered a planet made of solid diamond, and recently measured the mass of the universe, the baryon density of the universe. So we kind of weighed the universe with these high-speed signal processing instruments. So one of the problems that we have in CASPER, it's a big collaboration of about 1,000 people. We have a problem with newcomers coming in. It's a lot of work to get all this code running, and the problem is that the code comes from a lot of different places. You have to get some code from Xilinx, the Vivado stuff that compiles for FPGAs. You have to get some stuff from the MathWorks, Simulink. You have to get our open source libraries and tools, and they only work with very special version numbers and special operating systems. And so a lot of people kind of struggled getting all this stuff installed and working seamlessly with the right versions. So what PRP did, in particular, John Graham put this together, was make a portal so that CASPERites could just log into this, and all the tools and libraries would all be kind of working seamlessly together. And people can log in from all around the world. And we got permission from Xilinx and the MathWorks to let them use our licenses if they're part of the CASPER collaboration. And that makes it so much easier for newcomers or even advanced users to spin up all this stuff and compile their designs. And we're very grateful to PRP, and especially for John, to make that happen. We've been thinking about it for a long time, and John went to work and made it happen. And there's some really nice a talk that John gave. We have annual workshops, and you can go to this URL and listen to his talk. He also gave a tutorial and led people kind of work through it. And now what John and others at PRP are helping us do is not just put all these tools and software online, but some of our instrumentation and hardware online, so that people can run the tutorials and test their designs without having to buy the stuff until they know it really works well, and then they can go out and buy it. This is a new Seti project that we're working on, which PRP is also starting to help us with. It's called Panoceti, and it's a collaboration between UC San Diego and Caltech and Harvard and Berkeley. And this doesn't exist yet. This is an artist's conception, but you can see what we're trying to do. We're trying to look at many places in the sky at once. This has 100 telescopes poking out. Right now, we just have 2 telescopes poking out at Lick Observatory. But this is the kind of thing we're working on. And each telescope puts out about 100 gigabits per second. And PRP, and especially John, have been helping us figure out the architecture for this, how to get all that data, combine it into a cluster, and how to take all that data and handle these high data rates and keep track of the metadata in time series databases. And so that's kind of the new project that we're working on with PRP, and just launching that collaboration with PRP. I'm excited about this because we're exploring a whole new search space that nobody's really looked at before. And it turns out in astronomy, if you want to make a new discovery, about half of the discoveries are made in astronomy by just looking at something that nobody's looked at before. If you look at a new wavelength or a new size scale, or in this case, a new time scale, we're looking at events from nanoseconds up to milliseconds, and nobody's done that before. Typically, astronomers they open up their cameras and they integrate for minutes to hours. They're looking for faint things. They're not looking for these transient things. So we're looking at a new search space, and it turns out we might find something interesting just because nature seems to populate all of parameter space. We don't know why that's true in nature. We know why that's true in evolution, that if there's a parameter space where creatures can adapt and evolve and take advantage and eat there or stay away from things that might eat them. So in evolution, all parameter space is sort of populated, but we don't understand why that's true in nature, that all physical space at all time scales and wavelengths is populated. So we expect by looking at this new time scale that nobody's looked at before, we'll find something. And PRP is going to be there. So thank you.
Exciting. Really looking forward to all of that. Part of me thinks, oh, I hope we don't find anything or any ETs. And the other part of me thinks we should find some ETs. So watching you every day. Our next speaker, and by the way, if you have any questions for any of the speakers, we have a Q&A button down at the bottom of the Zoom window. Feel free to chat your questions in there, and we should have a little bit of time at the end to answer them, and the speakers can certainly go into that channel and answer them as well.